black hole physics conference here. So today I'm going to talk about more theoretical aspects of some quantum field theory in curved space-time, especially in the cosmology. And Monday I heard that John Wheeler had interest in this problem in mid-60s. When the universe has a curvature, when the universe is closed, then the curvature makes the universe fully collapse. So in this case, we can think about what happens to entropy, thermodynamic entropy, and this is a problem of thermodynamic arrow of time, because classically we can expect that this entropy should be time symmetric. This means that when the universe collapses, then the entropy should decrease. And this problem was raised by many people, and the first scientific treatment was raised by Gould. Later I'm going to show you I'm going to explain the history of this problem. And in my talk, I'll deal with a system with matter field interacting with gravity. Because gravity is a universal force, so there can be a universal interaction between matter and gravity. So this implies that particles and entropy can be produced through this parametric interaction. And from cosmological side, we may expect this kind of particle and entropy production may affect some scenario of this cosmology. The point of my talk is that when the universe collapses time symmetrically, then thus the entropy of this matter field should decrease again in time symmetric way. This is the question I want to answer in my talk. Here is the history of this thermodynamic arrow of time. In 58, Gould raised this problem, and he argued that entropy should decrease time symmetrically when the universe collapses. He argued this argument. His argument was based on classical treatment of this matter plus gravity system. And later, in 79, Roger Penrose gave a counter argument to Gould's argument. He just imagined that collapsing universe is a kind of some co-moving observer falling into a black hole. So from this co-moving observer's point of view, nothing happens to him. So we may expect, even when the universe collapses, we may not expect entropy decrease. This was the argument by Roger Penrose. And in 1983, Stephen Hawking gave another argument about this problem. And in 1983, he proposed some quantum model for cosmology. So using his quantum model, he concluded that the wave function of the universe has a CTP invariance. So from this CTP invariant wave function, he concluded that the entropy should be time symmetric. However, just immediately after his paper, Don Page gave another counter argument to his Hawking's argument, because there can be time symmetric wave function out of CTP invariant wave functions. So Page just argued that entropy can increase monotonically in time, even though the universe recollapse. And later, Hawking and others withdrew their first argument about time symmetric entropy, and he agreed that entropy can increase because as the universe expands and recollapse, there can be some growing mode of density, and this density oscillation may cause the entropy to increase in time. Here is my contribution to this problem in 94 and 95, and I worked on quantum models for gravity coupled to matter field, and by handling this matter gravity coupling system, we obtained the result that the entropy can increase always through the evolution of the universe, even though the universe may recollapse in future. And one of our results is that time symmetry may be broken due to this parametric interaction between matter and gravity. Today I'll give you a more better explanation for this process. As you know, gravity interacts universally with the matter. So just let me think about some model, gravity and the scalar field model, or gravity and electromagnetic field. And everyone knows that in plane Minkowski space-time, this is the field equation for scalar field or electromagnetic field potential. And when we construct a quantum field for this scalar field or electromagnetic field, then by introducing some creation and annihilation operator in some suitable Hilbert space or Hart space, and this is the quantum field for that in plane Minkowski space-time. However, in the Friedmann-Robertson-Walker universe, because we are interested in recollapsing universe, the matrix has some time-dependent scale factor. So the quantum field theory changes a bit. We have something like a damping factor here due to the expansion. Also, when the universe recollapses, it's kind of this term has the effect of pumping energy into the scalar field. So for this, in the Friedmann-Robertson-Walker universe, the quantum field changes a bit. I mean, here we have the solution. We should use the classical solution in the curved space-time instead of flat one. This is the only change. The particle production in curved space-time was first explained by Leonard Parker in 1968. He considered some gravity system which has two asymptotic regions, and in asymptotic region, his argument is that the vacuum solution in one asymptotic region can bear some particle state in the other asymptotic region. So we may gain some particle production when there is some gravitational interaction having two asymptotic regions. Anyway, we learned that in this kind of expanding universe, we have some kind of time dependency anyway. So this means that the quantum field theory in this universe should be non-equilibrium in its property. So we need a new method to treat properly this non-equilibrium quantum field theory before we give any argument about the entropy of this matter field. In the expanding universe, we have a time-dependent matrix through the scale factor of the universe, and therefore, we have effective some coupling constant depending on time. So actually, this is not a stationary system; it's a time-dependent quantum system. So we need to treat this non-equilibrium quantum system properly. And for instance, in the Friedmann-Robertson-Walker universe, and we'll assume a closed universe because we are interested in the collapsing universe at a later stage of evolution. And then, because we have a S3 topology, so we can expand the scalar field or vector potential for electromagnetic field and its conjugate momentum in terms of some Laplace operator on S3. Then this scalar field is equivalent to a collection of infinite number of time-dependent harmonic oscillator systems. And everyone knows that how to handle this kind of time-dependent quantum system, quantum time-dependent harmonic oscillator system instead of quantum field theory. So you may get much more physical intuition by treating this system instead of the original quantum field theory. And to get the quantum state and also the wave function of the matter field, you need to solve this quantum evolution equation. This is a functional Schrödinger picture for the matter field. And also, because we have a time dependency through the expansion of the universe, we need to solve the quantum Liouville-Neumann equation at the same time, but there is some underlying relation between these two equations, because whenever you have the solution for this quantum Liouville equation, then you can solve the equation for this time-dependent functional Schrödinger equation. And this argument was first given by Louis and Liesenfeld in 1969. He introduced some operator that satisfy this quantum Liouville equation for this time-dependent oscillator system. And in terms of this operator, he could find the exact quantum state, and the exact quantum state is nothing but the quantum state constructed out of these operators. And this was the key point of his method. So, because the scalar field is a collection of infinite number of harmonic oscillator, and we know also how to solve this harmonic oscillator system, so that we can find the wave function and quantum state to compute the entropy content of this matter field as the universe evolves in time. Here, we may introduce two operators, that is a pair of operators in terms of the classical solution. Where is it? Oh, here, yes. And we know how to solve this classical equation when we are given explicit form for the scale factor of the universe. And after we find these two operators, then we can construct the number state by treating these two operators just as creation and annihilation operator as an harmonic oscillator case. Now I give you a really simple explanation about particle and entropy production using quantum mechanical idea. Just let's just consider some simple time model here. We have a time-dependent frequency square, and for this time-dependent frequency square, now let's think, just consider step potential like this one. Then for quantum field theory, the right solution satisfying the appropriate boundary condition has this kind of some outgoing mode in at past infinity, and also some incoming light and outgoing light in time. This is the way to explain particle production in curved space-time. However, when you take a complex conjugate of this diagram, and also when you write time, when you interpret time as one space degree of freedom, then you have a really quantum mechanical scattering problem here. So this becomes incoming modes and reflection and transmitted wave. So from this analogy, you may find that this relation, this is nothing but it's a relation for Bogoliubov transformation. Now let's turn to more concrete model. This is an exactly solved model. Just to take after the similarity, you see scalar field or electromagnetic field in the Friedmann-Robson-Walker universe. We take some appropriate time-depending factor here, t squared. This means that the universe really expands. Then we can solve the classical equation. And in terms of this classical solution, we can really calculate the particle production and also the entropy production. The initial vacuum state is given by in terms of a cylindrical function, W here. And because when time is at past infinity, we should have only the solution for vacuum state. So this is the right wave function for that vacuum state. And however, when we evolve the system in time to go to future infinity, then the wave function has different form. And through the relation of this mathematical function, we found that the incoming state is nothing but the superposition of some particle creation part and particle production part. So this relation implies a Bogoliubov transformation. This following Bogoliubov transformation. So this factor mu k explains nothing but the particle production. We can rewrite this Bogoliubov transformation using squeeze operator. This is just to compute the particle production more efficiently. It does not have any meaning. However, it helps anyway when we do computation. So this Bogoliubov transformation, there should be some factor missing here. Oh yeah, I did not write. And anyway, in terms of this squeeze operator, the annihilation operator, in vacuum state, the annihilation operator for in vacuum state is the unitary transformation the other way. The annihilation operator in the out region is the unitary transformation of that by this squeeze operator. And there are some difference between ordinary quantum mechanics because quantum states depend on time. So this when we consider the full content of the quantum field, then we have non-unitary in equivalent representation, this means that the Hilbert space has differ from each other at each moment. So this means that the vacuum states at two different times are orthogonal to each other. This means that it should vanish. So this unitary in equivalent representation of the underlying Hilbert space implies particle production. As we see, when you calculate the number states in the out regime, then you get the particles produced through this parametric interaction. And now let me just skip that. More increasing our initial state is the thermal equilibrium state. Just assume that the initial states are described by this thermal equilibrium is a suitable temperature. Then we may use that Hilbert space to calculate entropy production. And through some computation, in the end we find that the entropy proportional to the initial entropy present at the in regime. And the conclusion is that the entropy always increase in time. Also, the entropy increase in proportion to the entropy present at the past infinity. Now let me go back to the collapsing universe. The classical equation motion is given by this form. So by rescaling, by redefining this classical field equation, now let's rewrite this classical equation just as it is a one-dimensional quantum system. And then using the same argument from quantum mechanics, we may find this kind of some reflecting coefficient. And this factor explains nothing but the particle production in the recollapsing universe. So even though the universe recollapses time symmetrically, we do respect to the maximum expansion of the universe, we always get some particle production and entropy production. This is the final concluding remarks. Entropy always increase. Entropy always increase in time. And we may consider some consequence of this particle and entropy production to cosmology. And one of them is that when the rate for entropy production for baryons and photons are different, then the present nuclear synthesis may be affected by this mechanism of entropy production. And there is a minor similarity to black hole physics. When we consider black hole formation, I'm not talking about stationary black hole. I'm talking about black hole formation by collapsing matter. Then we may expect a similar kind of entropy or particle production. Finally, even though it sounds strange to most of people, we may conclude that thermodynamic error of time may be originated from the expansion of the universe. This means that the experiments at this room may be affected by the expansion of the whole universe. So this is the end of my talk. Yeah. If your conclusion is correct, then can you
comment on the several papers that you mentioned in the beginning that the entropy, some papers show that the some entropy will decrease and the universe decrease. Okay.
The first few papers treat the classical system, so we have exactly time symmetric situation there. But from quantum mechanical point of view, we have a really time symmetry broken. So this is the quantum result, and we may expect this kind of mechanism to play certain role at the early stage of the universe, because there quantum effect may be important.
But when the universe concept that the far future, the quantum effect is not so great.
Maybe, but because classical universe is some semi-classical limit of quantum theory, some quantum model, so we may expect some kind of quantum interference effect to cause this entropy to increase in time. It's a quantum mechanical result, not classical one. But you may argue that our universe is classically, perfectly classical. That's okay. But when we include quantum effect, then it may change the result of this.
Any other questions?
It seems to me that you didn't consider the self-interaction of scalar field.
That's right. That's right. I just consider the fixed classical fixed background space-time because nobody knows the exact solution with the reaction by matter field to geometry. So I just consider the classical evolution of space-time.
Okay, let's thank the speaker again. We are well ahead of